Hello everyone, good morning. So I hope till now everything is clear. So before starting, everyone kindly comment that I'm fully audible and visible to you all. And this is your, we can say last class of your hydrology, in which we will be discussing mainly flood routing. Okay. First we will finish the topics which are remaining in flood, and then we'll move on to flood routing, and we'll discuss the techniques with the help of which we'll do flood routing. Okay. So kindly comment that I'm fully audible and visible to you all. Okay. Yes, it is fully audible now. Okay. So in last class, we have discussed about, let me tell you what we have discussed till now. Yes, wait a second. So in last class, we have discussed the estimation of peak flood discharge. Okay, why we are interested in finding peak flood discharge? We have discussed this, and how we find it. Okay, what are the different methods to find your peak discharge, that we have discussed. Okay, so I told you that in physical indication of past flood, we analyze the past records. In envelope curves, we took some similar catchment areas, basins, to our catchment area, and we have drawn some patterns, and based on that we have decided the peak discharge. Okay, then we have used UH method. Then empirical formulas were there. I told you about empirical formulas. Okay, see, these were the formulas. Dickens formula was there, Reeves formula was there, then your English formula was there. Many formulas were there which we have discussed in the last class. Then rational method was there. Then we have discussed rational method. I told you this was the fifth method. We discussed rational method, and today we are going to discuss the frequency analysis method. Okay, so we discussed rational method, in which we discuss what is time of concentration. So time of concentration means the farthest, the maximum time which your surface water takes to reach the outlet, maximum time. So obviously the water which is at the farthest point, that will take the maximum time, yes or no? So maximum time required by surface runoff to reach the basin outlet is your time of concentration. And when the duration of rainfall is greater than or equal to time of concentration, then you will observe that maximum runoff, surface runoff will occur, because entire catchment area will start contributing. So based on this, we have evaluated a formula which is QP equals to 1 by 36 CIA, where I is intensity of rainfall in centimeter per hour, and A is area of basin in kilometer square. Okay, and we have solved one example also, with the help of which you can easily find your peak discharge. After this, we discussed some empirical formulas which are not so important, but yes, we have discussed some empirical formulas with the help of which we can find intensity, and that intensity we can use in our rational formula to calculate the peak discharge. This we have discussed. Then we have we came up to the topic of frequency analysis, in which uh, if we have to predict future floods in our river, if we have to predict future floods in our stream, okay, so how we'll do it? If we want to see, let us say we have a river, and in that river I want to find, in this river I want to find what will the discharge corresponding to return period 500 year. Okay, how I will find such kind of discharge? So if you want to find a kind of discharge with a certain probability, with a certain return period, okay, in your river, then how will you do it? For that we are going to understand a method today. For that we are going to discuss a method which is known as your frequency analysis method. Okay, in this frequency analysis method, what we do, we analyze the past data. Okay, we analyze the past data and predict the future flood events. Okay, so for this, firstly we have to collect the data. Yes sir. So data can be collected either annually or partially. Annually means we are taking the values of annual maximum flood in 1 year. What is the maximum value of discharge? If we take that value, okay, and plot it in or you can say, or plot it in the sequential manner, or write it down in a chronological order, then I will call that data as annual data. Because for each year, what is the highest discharge? This is the highest discharge in first year, this is the highest discharge in second year. This, if we'll plot them, when we will get a data. So that is our annual series. So we do this when we want to evaluate floods of large return period, such as I want to find flood of I want to find a discharge corresponding to a return period 500 year. Obviously this will be huge, because this is a kind of discharge which comes in river only once in 500 years. So it will not be small, it will be a very great discharge, it will be a very big discharge. Okay, so then I will use this data. But if I want to find floods of a small return period, such as 5 years, 10 years, okay, tell me the value of discharge which will return in 5 years only. So for that I will use my partial data series, in which I will note down all the peak values, which my river has experienced in its lifetime. Okay, So we'll note down the peak values of your river in your peak in its entire lifetime and plot the data. Now, with the help of that data, we are going to find standard deviation and mean. Okay, if you have data, let us say 500, 550, and let us say you have 30 points, and let us say you have 50 points, 100 points. So can you simply find the mean? Yes. Simply sum up all the discharges and divide it by the n value, and you will get the mean value. Okay, mean is very simple to find. Mean is very simple to find, and similarly, you can find the standard deviation. Standard deviation we have already discussed how to find in your optimum number of rain gauges in the first chapter. Okay, in the second chapter, there I already told you how to find your mean of the variate. Okay, so this is it. Now Gumbel's method. Gumbel's method is what? Gumbel's extreme value distribution. What is this method exactly that we are going to discuss today? Okay, so what this method exactly is that we are going to discuss in this class. Okay, wait a second. What exactly Gumbel method is that we are going to discuss in this class, and we'll also solve some questions. Okay, we'll also solve some questions, so there is no need to worry about it. Okay, so I will tell you the exact method. I will tell you the exact method how to utilize Gumbel's method to find the peak discharge or to find the future flood event corresponding to a given written period. How to do that? Okay, how to do that? I'm going to tell you that. Okay, now sir. So in Gumbel's method, sir, there are basically three equations. Okay, in Gumbel's method, there are basically three equations. This is the first equation. In first equation, we have to find the discharge. See, we will take the discharge as x. Okay, because x is an unknown. X is an unknown, and we want to find it. Sir, I want to find a discharge corresponding to a written period t. Corresponding to written period t. Yes or no? Yes, sir. I want to find discharge corresponding to written period t, and it is equal to x mean plus k times sigma. Okay, it is corresponding to x bar plus k times sigma, and sigma can be calculated corresponding to n minus 1 or n. No issues in that. Now, second equation is yt equals yn plus ksn. Now this is the equation given by Gumbel. Okay, some another equation. We will discuss the meanings in this one. Don't worry. How to find yt? See, you need to understand from the data which we will be having, from the data which I will be having. Okay, which I have studied for the last 50 years or 100 years for my river. I will use that data, and I will find x bar and sigma. Now, in order to find the discharge, I only want the value of x. I only want the value of, sorry, k. I only want the value of k. Once I get the value of k, which is a frequency factor, I will put it here and get the discharge. Now, one more thing. Sir, this is with me. I will find this with the help of data, which I have studied from your, or which we have obtained from your past records. Okay. And k is a frequency factor that depends on what kind of discharge you have. Let us say if you want to find discharge of 50 years, let us say if you want to find discharge which is returning after every 100 year, let us say you are interested in finding discharge which is returning after every 500 year. So the k value for this one will be less. Okay, let us say 0.6 or something. So for 100 years, if discharge is returning after every 100 year, obviously it will be big. Obviously it will be of huge magnitude. Then obviously k will be large, because then you will add a bigger, you can say a bigger value here. Okay, for this one k will be even higher, like this. So frequency factor is a factor. Yes sir, frequency factor is a factor which is proportional to written period. If written period is more, then obviously this frequency factor will be more, and if this frequency factor will be more, I will put this higher value here and will get a bigger discharge. This is discharge. Yes or no? Tell me this thing. Sir, I will get a bigger discharge. Understood, sir, clearly? So I think it is very, very clear that we are interested in finding this with the help of this equation. But I have x bar, I have x n minus sigma n minus 1, but I don't have k. So from this second equation, you are going to find k. From this second equation, you are going to find k and put this value of k here. Okay, but how to find this k from second equation? So tell me that. Okay, so if you want to find k, from the second equation, first you want to find the value of yt. Okay, if you want to evaluate yt, what you are going to do is, you have to use this formula minus ln t upon t minus 1. You have to use the formula ln t upon t minus 1. Now let us write the meanings of each and every one so that you are able to understand. So you will put yt from here. Yn Sn will be the values which we will read from Gumbel's table corresponding to data. Okay, and once we have yt, once we have yn, once we have Sn, I will get the value of k, put the value of k here and get the answer. This is the ultimate process. I will solve one question, don't worry, just be patient, you will understand. Okay, now what is xt, sir? Sir, xt means value of variate. Xt is what? Sir, xt exactly is value of variate, or you can say a variable quantity. Xt is value of variate or a variable quantity, and in our case the variable quantity is discharge. It is peak discharge. Okay, with a return period of t. With a return period of t. This is xt. Now what is x bar? X bar, sir, is mean value of variate. X bar is what? Sir, mean value of variate, which is nothing but simply what I have to do. If I have data, I will sum up all the discharges and divide it by n. How I will get this? I will get this from annual series. Sir, you told me we have an annual series, we have a data in which we have written down all the peak discharges corresponding to a given year. Let us say for 2020 discharges this much, for 2019 discharge this much. So you have a table. So from that annual series or from that table, you are going to find the mean. Okay, simply sum all the discharges and divide by 50, 100, whatever number of data points you have, you can divide it from there. Okay. Now this one, next is sigma n minus 1. Next is sigma n minus 1, which is standard deviation. Standard deviation of variate. How you will evaluate this? How we will evaluate standard deviation? So formula for this standard deviation is under root. Now you have to subtract first all the values from mean. You have found out the mean, subtract all values from mean. Okay, get the deviation, square it, and add all the deviations from mean and divide by n minus 1 and then take under root. So this will give you your sigma. This will give me the sigma. Okay, sir. Now what is yt? Yt is a reduced variate according to Gumbel. Gumbel introduced that if I want to evaluate discharge, see, he derived a new equation. According to him, see this. So if I want to reduce it, if I want to convert it, I will convert this. See, this is very similar to this one. Yes or no? This second equation is similar to the first one. We are actually interested in first one, but I will use the second one, which is reduced by Gumbel. So this is actual variate discharge, actual variable because discharge will vary, and this is reduced variable by Gumbel. Okay. So this is a converted variable. This is a reduced variate. Okay. Now what is Yn and Sn? Yn and Sn are mean and standard deviation. Are mean and standard deviation. Are mean and standard deviation of reduced variation. Okay. So sir, what you are saying overall? That we have reduced the equation and we have reduced our data, and according to Gumbel, so from his side we will obtain this mean and standard deviation of reduced variate. So variate is now reduced, and now we will obtain the mean and standard deviation for reduced variate. Okay, and we will find the value of this reduced variate with the help of this formula. Put it here, put Yn Sn and get the value of k, and put it here and get the value of discharge. This is the ultimate thing, and k is a frequency factor. Okay, k is a frequency factor. Okay, sir. Now how to find the discharge? We'll understand the exact procedure, but let me tell you how to get the value of Yn Sn and the exact procedure. then we will able to understand how to find the discharge. Then we'll easily understand how to find it. Okay, now this yn and Sn, this mean and standard deviation of reduced variate, okay, are function of n. That's why I have written n in subscript here. We have written n here because yn and Sn, mean and standard deviation of reduced variate, are function of n only. Okay, number of n means how much data you have, how much data you have for your number of years of record. Let us say you have collected data for 50 years, so n is 50. Let us say you have collected data for 100 years, so n will be 100, like that. Okay, so corresponding to a given n value, you will find the yn and Sn value from Gumbel's table. Okay, you will find yn and Sn value from Gumbel's table. However, if n is large, generally greater than 200, if n is large, generally greater than 200, then in that case yn and Sn value becomes constant. Then yn value will tend to 0.577 and Sn value will tend to 1.2825. Sn value will tend to 0.2825. Okay, so this is for infinite size sample. This is for infinite size sample. Now sir, tell me the exact procedure. Okay, now tell me the exact procedure how to follow the and solve one question, so that we are able to understand how this method exactly works. Okay, so the steps which are involved in finding the discharge using Gumbel's method, I will write down the steps here. Simple, very simple, 3 to 4 steps are there. The very first step is obtain data, collect the data of your river, such as for 50 years. Okay, so from 2020 to 1950 you have data. Every year you are having the highest discharges like this. So this is your data. This is your data of discharge for your river. Okay, from this data, first obtain the data and simply find its mean and sigma n minus 1, simplified mean and standard deviation for the given data. Simplified mean and standard deviation for the given data. This is the first step. Second step is determine. See, first step is to find this. Understood, sir? Now, second step is to find this. So, determine yn and Sn. Okay, mean of reduced variate, standard deviation of reduced variate corresponding to n. Okay, using Gumbel's table. We will go to the table corresponding a given value of n. Let us say n is 50 years, 70 years. Let us say you have record of 70 years. So corresponding to 70, you will read the value of yn and Sn from the table. But in examination, this yn and Sn will be given to you using table for given value of n. N is what? Sample size. N is what? Number of years of record. See, the larger the data you have, the correct results you will get. Okay, more the data, the correct answer I will get. Okay, now I have to find yt. After this, so this is done in the first step, this is done in the second step. Now I will find yt from this equation and put it here. So this is also done. Then in fourth step I will find k and I will put it here and find the x. Okay, simple, basic. Okay, so now find yt corresponding to a given written period. After that, find k using equation 2. Okay, if you see equation 2, if you want to find k is what? Yt minus yn upon Sn. K is what? K is what? Yt minus Yn. See, Yn, Sn you have obtained in the second step. Sn and Yn you already obtained. Yt you have obtained in the third step. Put Yt, Yn, Sn, get the value of K. Yes or no? Put the value of K. And from this value of K, what I will do now, sir, in the last step, I will find the discharge. I will find the discharge corresponding to return period T using equation 1. Okay, how to find xt? Simply, sir, x mean x bar plus k you have obtained now. Put the value of k into sigma n minus 1. So this mean and standard deviation you have already calculated in the first step. Multiply by k and get xt. Okay, multiply by k and get the value of xt. So this is the steps. These are the steps which you have to do. Okay, so have you understood the steps? Now what I will do after this, I will take up a question so that everything is very, very clear to you. Okay, we will take one question. With the help of that, everything will be perfectly clear to you. Okay, so I will take up an example. So this is a data you can see in this question. Let us read out this question and try to solve it. Okay, so this question is saying, sir, an analysis of annual flood series. What is this meaning? The meaning of annual flood, see, they have analyzed one flood series in which, let us say, they have data of, let us say, 50 years or whatever. Okay, they have data. This is, let us say, 2020, and in this peak discharge, let us say it is 450, like this. Okay, then we have 1020 meter cube per second, like this. You have discharge values for different years. So this is your flood series. Okay, sir, they have analyzed it and they indicated that mean value, if you take the mean value of this one and standard deviation of this data, you will get it as 940 and 203. They are saying it. So simply in the very first step, mean is given to you. Okay, what things are given to me, sir? Sir, first thing, that mean is given to me. Mean is 940. Yes or no? Tell me. 940. And second thing is sigma, which is also given to me, which is 203. Which is 203. Okay, 203 meter cube per second. So this is your standard deviation. This is your mean, respectively. Now, what is the magnitude of a flood of return period 500 in this stream you want to find? See, you are interested in finding here. First, you need to understand we are interested in finding a discharge corresponding to return period 500. Yes or no? Corresponding to return period 500. Okay. So this we want to find here. Okay, sir. We have to find discharge. Assume that annual flood series follow Gumbel distribution. Okay. And the sample is very large. See, one thing you want to understand from here is that when sample is very large, then the value of y and Sn we have already noted down. Okay. So I will write one point here in this. See, we have to apply these 5 steps basically. Yes or no? Yes, sir. We have to apply these 5 steps. So if I want to apply these 5 steps, I will go step by step. So obtain data. There is no need to obtain data because they have already analyzed the flood series for you and they have given you mean and standard deviation directly. They have directly given to you. Okay. Now determine y and Sn. So y and Sn will be what? Sir, since n is equal to infinity, or you can say you have data, you have very large data, you don't have 50-year data, but you have data which is, let us say, for more than 200 years. You have a very large data. So for that, Yn and Sn will be constant and it will be this much. Okay, so I will write here one point. Sir, since sample is very large, or I can say since n is almost tending to infinity, okay, I will write the value of Yn as 0.577. It will almost become constant, and Sn is 1.2825, and Sn is what? 1.2825. Simple. Understood, sir. Now if I want to find Yt, now the third step is find Yt for a given t. So I will use this formula to find Yt. Okay, simple. No problem. So yt is minus ln upon into minus ln t upon t minus 1. So I will use this formula and find the value of yt. Okay, sir, I will use it. So minus natural log into natural log. See, the given t corresponding written period is what? 500 years. So 500 is a huge written period. Okay, so this is equal to what? 500 upon 500 minus 1. 500 upon 500 minus 1. So this will be equal to, if you will solve this in your calculators, you can find the value of 500 upon 499, divide it, take natural log, whatever value you get, take natural log again and multiply it by minus 1. So you will solve and you will get the value equal to 6.21. You will get the value equal to 6.21. Okay, simple. So now, sir, we have obtained the value of yt. Now what next? I have to find k using second equation. Okay, k is what? Now, sir, what is k? If I want to find k, see, sir, I have this equation. I have yt equals yn plus ksn. This was the second equation. So if you want to find k from here, if I want to find k from here, so the value of k is what? Yt minus yn upon sn. Yes or no? Tell me. Yt minus yn upon sn. Now what is yt? Yt is, sir, 6.21. Okay, sir, no problem. Yn is 0.577 upon Sn is what? Sn is 1.2825. Divide it and get the value of k. So when you divide it, you will get the value of k or frequency factor as 4.39. Okay, it's a huge frequency factor. Okay, it's a huge frequency factor which depends on yt. More the written period, more the value of yt, and more the value of yt, more the value of k. Okay, so simply, sir, you are saying that this yt value is proportional to t. If written period is more, yt value will be more, and if yt value is more, you can understand k value will be more, and if k value is more, sir, my discharge will be more. Okay, if k value is more, my discharge will be more. So now in the last step, I am simply going to find the discharge. Okay, so if I want to find a discharge corresponding to written period 500, what I will do, I will simply find it from the basic equation. Okay, this was the basic equation. I will use this first equation and simply find the discharge. Okay, so x mean is given to me as 940. K we have obtained as 4.39 and sigma is given to me as 203. And sigma is given to me as 203. When you will multiply it, you will get the answer as 1831.17 meter cube per second. Okay, so this is the discharge which will come in your river once in 500 years, like this. This is the discharge which will come in your river once in 500 years. Okay, so this is the you can say question of Gumbel's distribution, in which we have predicted a future flood event corresponding to a given written period t from the past record. If we have a past record, if we have a past flood series, so from that I am going to obtain my future flood event that we have done here. Okay, this we have done here. Have you understood this? Tell me, is this thing very clear to you? So this is the you can say method with the help of which you will solve Gumbel's question. So I hope it is very clear to you. I hope this is very clear to you. Yes or no? Tell me. Tell me if there is any confusion. If you want to ask any doubt, you can ask it here. I hope you have understood this method very clearly. Simply these equations are there. Meaning of everything is written to you. Question steps are also given to you. Okay, using these steps, simply you can find the answer. Okay, so one thing we have understood here. One thing I have understood here, sir. What is that logic? Sir, if written period is more, simply, sir, you will see if written period is more, sir, yt will be more. Okay, and if yt is more, then obviously k will be more. And if k is more, sir, obviously the discharge which I am finding, that will also be more. Okay, so this is the logic which you have to understand here. Okay, so written period more the discharge you will get. Okay, because discharge you have to ultimately find from this equation, and k will be more, so find yt, put it here, write yn sn, find k, and from k get this value. So this is the simple step. Okay, so remember it. Understood. Now we'll move on to the next topic, which is your flood routing. Now we'll move on to the next topic, which is your flood routing. I will tell you what is the exact meaning of flood routing and why, how we will finish it. Okay, just wait a second. Just wait a second. Okay, so I hope Gumball's method is clear to you. There is no doubt in this chapter. Okay, now we are going to discuss your flood routing. Okay, what is flood routing? What is the exact meaning? Sir, tell me the meaning of flood routing. See, flood routing is very simple. See, flood routing is a very simple technique. Let me tell you with the help of an example. Okay, what is the meaning of flood routing? See, you need to understand one thing. Let us say we have a river. Okay, sir. And on this river, we have constructed a dam. Imagine you have constructed a dam on this river. So if you have constructed a dam on this river, a reservoir will be developed behind it. Reservoir means a large, or you can say large volume of water will be stored behind it. Okay, sir. This we have understood. And let us take a section here. Okay, listen very carefully. This is a important technique with the help of which you can predict future floods. Okay, sir. So this is, let us say this is your section 1. Let us say here we have a section 1. And let us say here we have a section 2. Okay, understood, sir. This is my section 1 and this is my section 2. And let us say this is the down, see, water is flowing in this direction. Okay, water is flowing from upstream to downstream. This is my upstream section and this is your downstream section. Okay, sir, this I have understood clearly. Simple thing. Now what will happen if a flood will come? Let us say a flood is coming, a discharge is coming, a high magnitude of discharge is coming. So it will enter section 1 first. Yes or no? And the after moment it will enter your section 1, after some time it will reach your downstream section 2 also. But it will take certain amount of time. Yes, sir, it will take time. Let us say this distance is 30 kilometers. Let us say this distance is 50 kilometers. So obviously rivers are very long. Okay. So from one point, if flood enters, it will reach a downstream point after some time. But if I have the discharge values, let us say a station was here, and at this station, at this, you can say inflow section, this is your inflow section. This section I will call it as inflow section. First section. Let us say let us say I have this discharge value at this section. So with the help of this discharge values, can you find the discharge values that are going to occur at some downstream section after some time? Can you get these discharge values? What? See, if flood, let us say flood has come at this section. So obviously it will be going to impact your downstream section also. But after some time, obviously after some time, because it has to travel a distance. Okay, that flood, that water has to travel some distance. Then it will impact your second area. But if from this data, if from upstream data, I am able to predict what discharge is going to occur at section 2, okay, then obviously you will get some time and you can do evacuation there. Okay, we will be having some time and I can predict the flood future flood here. So I will get some time and I will save it. Okay, so flood routing is a technique in which I am interested in finding the discharge at some downstream section. Yes or no? I am interested in finding discharge at some downstream section. Okay, so in this technique, what we have basically is you have a hydrograph. Listen very carefully. You have a hydrograph. You have a hydrograph at inflow section. You have inflow flood hydrograph. You have inflow flood hydrograph at section 1. Okay, your hydrograph means discharge versus time graph. Okay, you have discharge versus time graph here at inflow section at section number 1. Okay, you have discharge versus time graph here at upstream section. Let me say this is section number 1. Now obviously this water will reach, okay, now while discharge will increase at section 1, obviously this water will reach your downstream section 2. Let us say this is your downstream section 2. Okay sir, yes. So we are interested in finding, sir, we are interested in finding this flood hydrograph. Okay, this flood hydrograph we don't have. Okay, this flood hydrograph will be called as this flood hydrograph, which is going to occur at section 2 or at downstream section, that is known as outflow hydrograph, because once discharge will reach there, it will move out, from this reach. This is a reach. Okay, this is a reach of your river, or up you can say a portion of river. So in this portion of river, water gets entered from this section and exits from this section. So I will call this flow as inflow and I will call this flow as outflow. Yes or no? Yes or no? So this is my outflow hydrograph. Okay sir, so this is section 2. This I want to find out. For the time being, I don't have it. I want to find this. This is a question mark. Okay, I want to find the hydrograph at section 2. So this is at section 1, this is at section 2. I want to find it. So simply sir, you are saying flood routing is a procedure or is a technique in which I will write one basic definition here of flood routing so that you are able to understand it. See, it is a procedure. Okay sir, it is a procedure whereby the shape of flood hydrograph, at a particular location, where the shape of flood hydrograph at a particular location, of a stream, is determined from the known or assumed flood hydrograph, at some location upstream. Okay, so from some location upstream, okay, from some location upstream at which I know the flood hydrograph, I will find the flood hydrograph at the downstream section. Okay, so at some particular location of a stream or some downstream section, I want to find the discharge values, I want to find the hydrograph. Okay, so this is your flood routing. Okay, so why this is done, sir? Why this is done basically? So this is done to establish, you can say this is done to establish a flood peak. You want to find what highest value of discharge will be crossing this section. So for that, I am able to prepare my dam section. Okay, that's why. Simply you want to find discharge value, and secondly, you will be able to predict how your river behaves, will behave when a flood value is there, when a flood wave passes from here. Okay, if a flood wave will pass from here, how your river will behave. With the help of this outflow hydrograph, you will be able to predict. Okay, secondly, you can find the capacity of your spillway. Okay, spillway is what? Spillway is a, you can say, a valve or a gate which is provided at the top of the dam, so that it acts as a safety valve. Basically, when your extra water is there, that extra water, surplus water, is removed from this spillway. So if you want to find the capacity of spillway, you can do that with the help of this, because now you will be able to understand how much maximum discharge will be here at section 2 using this technique. And if you will find it, what you will do, you will be simply designing your spillway capacity. Okay, so these are some you can say applications of flood routing. Okay, what you can do, you can also find, let us say you want to protect this reach from your flood. So what you will do in this reach, you will construct embankments. Okay, let us say this is river water, and obviously now flood water is more. So what you will do, you will increase the height of your embankment. Okay, you will increase the height of embankment. How? You will increase the height of embankment using your mud, obviously, and how much value of mud I require, how much is should be the height of my embankment on the sides of river, that I can evaluate because I have the discharge now. Okay, so simply by predicting what discharge will happen at some downstream section, I can do flood protection. I can do flood protection works. I can do the solve the capacity of, okay, I can design the capacity of spillway. So all these things you can do. Okay, simply it is a protection method. So I hope this is very clear to you. Now the techniques which are involved in flood routing. So basically in this we have two techniques, but the first one is more important, and questions if there are in exam will be from first topic only. So first technique is lumped routing or hydrologic routing. So in this technique, what we are going to do in this technique, we find out discharge, which will be a function of time only, See, you can see from this graph also that discharge is varying with respect to time. This is your flood hydrograph, okay, at any given location, and location is fixed, that is section 1 and section 2. Location is fixed, we are not changing the location. Okay, so this is your lumped routing or hydrology routing. One more thing, the equation that we use in this one, okay, in this technique, we only use continuity equation. Okay, in fluid mechanics you must have studied about you must have heard about this equation, which is your continuity equation. Okay sir, so in this technique we will use continuity equation, but in this distributed routing or hydraulic routing, what we'll do in this, we find out in this technique we find out discharge. Okay sir, and that discharge will be a function of space and time. Okay, so I can say it will be a function of, q is a function of, x is space, q is a function of, see, for different sections, see, this will be the value of x. Okay, x will change. This is 100 meters, 200 meters, like this. Okay, so when x changes, obviously discharge will also change. You can see when you will move ahead from inflow section, then at that point of time discharge will be less. It will be highest at inflow section. Okay, so q is a function of space and time. Q is a function of space and time. And one more thing, in this technique we use two equations. In this technique we use two equations. One is your continuity equation, and second one is your momentum equation. If we combine both these equations are known as Saint-Venant's equation. If we combine both these equations, it is known as Saint-Venant's equation. Okay, so I hope these are, see, forget this because this is not important, this is only important. So I will first tell you what continuity equation is. Okay, so the basic equation which we use in flood routing is your continuity equation. You need to understand this. Equation. Okay, continuity equation we have already understood. Simply it is your water budget equation, nothing else. Okay, so how we will write this equation? See, inflow minus outflow is equal to change in storage with respect to time. You know this. This is only your continuity equation. Okay, see, you need to understand. Let us say we have a inflow flood hydrograph. Okay, let us say we have inflow flood hydrograph. So at this section, this is my inflow flood hydrograph. Okay sir, no problem. And let us say if I want to find outflow flood hydrograph, and let us say this is your outflow flood hydrograph. Understood sir? Now what I will do, I will take a time duration here. Delta t. Okay, now on inflow hydrograph I will take 2 points, point number 1 and point number 2. Okay sir, similarly I will take 2 points on my outflow hydrograph, point number 1 and point number 2. Okay, sir. Now the value of inflow at time t equal to 1 will be I1, and value of inflow at inflow hydrograph at time t equal to 2 will be I2. Similarly, on outflow hydrograph, the values I will be having are O1 and O2 corresponding to different times. Okay, so see, you can say the discharge is increasing. So what discharge I will write? Will I write I1 here or will I write I2 here? So if you want to write the inflow discharge here, what I will do, simply take the average value of I1 and I2. Simply take the average I1 value of I1 and I2. So I will write here for, so I will write one point here for a small increment in time. So I will write here one point for a small increment in time, delta t. Okay, I will take the values, I1 plus I2 upon 2. Okay, subtract it O1 plus O2 upon 2. See, I will take average values. I1 plus I2 upon 2 is average discharge in this time interval, and O1 plus O2 upon 2 is average discharge in this time interval for your outflow hydrograph. Subtract it and get it equal to your change in discharge. Change in discharge is storage 2 minus storage S2 minus S1 upon T2 minus T1. This will be your delta S. See, delta S, you want to get, if you want to find delta S, how you will get it? See the area under the curve. If you want to find what volume of water has stored when your water has entered, it will be your this area, and what volume of water has exited your system is this area. So from this total area, subtract the area under your outflow hydrograph, you will get the water amount, how much water has got stored in the system. Okay, you need to understand, let us say we have a box here. Some water is getting entered and some water is getting exited. So it is getting entered, it is getting exited. So in t amount of time, if you want to evaluate how much is the volume that has entered, what you will do? You will integrate and find the area. And if you want to know what volume has exited the system, you will again integrate this graph, because this is the exit graph, this is the entry graph. Okay, so what I will do, I will integrate this area, integrate and find this area, and I will find this area, subtract it and get the change in storage that has happened in time interval delta t. This is delta t. This is your delta t. Okay, so in delta t amount of time, how much volume water has entered and exited, that I will find here. Okay, so if I want to show this area, if I want to show what this is representing, this is equal to this. This will be the middle area. This will be the middle area. Yes or no? This area. This area is being representing your S2 minus S1. Okay, so if I want to write the values, see, I1 is what? I1 is inflow at time T1. I1 is what? Inflow at time T1. I2 is what? I2 is inflow at time T2. O1 is what? O1 is outflow at time T1. And similarly, O2 is outflow at time T2. Okay, so these are your values. Now S2 S1 is what? S2 S1 is that when you are at time 1, some storage will be there. Okay, storage at time T1, storage at time T1, and S2 is what? Storage at time T2. Obviously there will be change in storage. Okay, when time will change. So let us say at first hour we have 500 meter cube water in our system. At second hour the volume of water is 400. So what is the change here? What is the change in storage? 100. What is the change in storage? 100 minus 100. Okay, system has depleted some water, so I will write minus 100 here. So this is your basic continuity equation which we'll use here. Okay, understood, sir. Now we also have a momentum equation. Which is not important, but yes, I will tell you because you must have seen this momentum equation in your open channel flow. Okay, you must have seen this momentum equation in open channel flow. So let me write this momentum equation. This is del v by del x plus v by g del v by del x del v by g plus 1 by g del v by del t del U by del T is equal to S naught minus SF. Okay, so this is your momentum equation. Okay, forget it, it's not important, so we are not going to discuss it. Okay, so these are basically two equations which are used, but only the first one will be important because we will be discussing questions or everything from your first topic only. Okay, now flood routing or the prediction of discharge can be done. Prediction of discharge, sir, can be done either in reservoir. Okay, either in reservoir where we have huge amount of water stored behind the dam. Okay, sir, this prediction of flood can be done. See, the example which I have told you right now, is your reservoir routing only, because see, behind dam we have a huge storage, we have a huge reservoir, and in that we are predicting the downstream discharge. In that we are, if we want to find your downstream discharge, so that is your reservoir routing. So storage, or you can say reservoir routing, this is your reservoir routing. Or you can do routing in directly in your river, or you can do reservoir routing in your channel itself, in your river itself, without any dam or something. So that routing is your channel routing. See, channel routing means a river is there, at section 1 you have the hydrograph, but at section 2 you want to find it, at downstream section you want to find it without any reservoir or dam on it. So that is your channel routing. Okay, this is your channel routing. Now what are the various methods? What are the various methods of reservoir routing? Okay, what are different methods of reservoir routing? First I will discuss reservoir routing, then I will go to channel routing. Okay, channel routing is more important. Okay, three methods are there in reservoir routing. The first one, three methods are there. First method is modified pulse method. First method is modified pulse method. Then second method is Goodrich method. Second method is Goodrich method. Third method is, many more are there, not so important. Okay, I'm just telling you so that at least you must see the names. This chapter is having very least weightage, but yes, still I am telling you some theoretical points so that if something is there in examination you are not unaware of it. Okay, so modified pool, Goodrich method. Okay, these are basically graphical methods. On a graph paper I will plot inflow hydrograph, and from there I will try to get your outflow hydrograph, and this is your numerical method, numerical approximate method. This Runge-Kutta method you must have heard about in your mathematics. Okay, now what are these equations? So we need to remember these equations, modified pool and Goodrich method. Okay, once they have been asked in your engineering services preliminary examination. Okay, so these are various methods of reservoir routing. And see, one more thing, we will only discuss hydrologic technique, we are not going to discuss hydraulic routing. This is not a part of our syllabus, so we are only interested in hydrological routing. So what I will do reservoir routing hydrologically, and I will also do channel routing hydrologically. We are interested in hydrologic routing only. Yes or no, sir? We are interested in hydrologic routing only. So I am going to tell you the methods of reservoir routing. See, this is reservoir routing, but hydrologically. We are going to do reservoir hydrological routing. So if we are doing hydrological routing, I will use only continuity equation. Yes or no? Tell me, if I am only doing reservoir routing hydrologically, so I will use only continuity equation. No, not tell me. I will only use continuity equation. This is my continuity equation. Okay, this is my continuity equation. So tell me these two equations, modified pool method and Goodrich method. So in this method, what we do basically is, this was our equation, I1 plus I2 by 2 minus O1 plus O2 by 2 equals delta S upon delta T. Yes or no? This was the equation. Now what I will do, I will rearrange it. Delta T will be multiplied here, this. Okay, so I will rearrange it and write it like this. This was our continuity equation. I will rearrange it and write it like this: delta T plus S1 minus O1 or Q1 delta T by 2. Q1, see, I1 and I2 are divided by 2. Q1 and Q2 are also divided by 2. Okay, similarly here we have S2 minus Q2 delta T divided by 2. Like this you will write. Simply you have rearranged it. Okay, simply you have rearranged it. This is an unknown factor. This is an unknown term which you will evaluate, and these are the known terms. So how this method exactly works, this you will get to know when I will tell you Muskingum equation. Okay, simply remember the equations for as of now. Simply remember the equations as of now. When we will discuss the procedure of Muskingum, you will understand how this procedure also works. Okay, so don't worry. I1 plus I2 2S1 upon delta T minus Q1 equals 2S2 upon delta T plus Q2. This is unknown. This is unknown. This is unknown. So this is your second equation, Goodrich equation. Okay, not so important, but yes, still I have told you. So I hope this thing is clear to you. This is done. Now, after this, wait a second. Let us solve one or two questions which have been asked in your examination. Let us solve those questions. See, these are reservoir methods. The main thing is channel routing. The main thing is channel routing. So before that, answer these two questions first. Before that, answer these two questions first. Before that, answer these two questions. Yes. See, the answer to this one is, see, they are saying the hydrological flood routing methods use which kind of equation? They use, basically you need to understand in fluid mechanics and in OCF. In fluid mechanics and OCF, you have basically three kind of equations. Okay, you have three kind of, let me tell you those three equations. One is your continuity equation. Okay, continuity equation. The second equation which we use generally is your force equation or momentum equation. Okay, which I have also told you in differential form. And the third equation is your energy equation. Okay, in which Bernoulli's principle you must have heard about. Okay, so that is your energy equation. So basically the hydrological flood routing methods use not energy, it does not use energy equation, momentum and continuity equation, yes, motion, continuity, but in hydrological, see, in hydrological method, not hydraulic. I have told you one thing, that in hydrologic method, this question has been asked once in your examination. In hydrological method, we use only what equation? Sir, we use only continuity equation. And in hydraulic method, we use continuity, momentum both, no energy equation. So sir, if you want to answer this question, I will say the hydrologic flood routing method only use which equation? Sir, equation of continuity. Yes or no? So D option will be correct here. Okay, is this thing clear? So D option will be correct here. I hope this is clear. Now the second question which is, tell me the answer to this one. Saint Venant equations for unsteady open channel flow. Unsteady means the discharge is varying with respect to time. See, if discharge is constant with respect to time, I will call it as steady. But if discharge is varying with respect to time, I will call it as unsteady. Okay, I will call it as unsteady. So in Saint Venant equation, I told you the second method, hydraulic routing. In hydraulic routing, sir, I use momentum and energy. No, momentum continuity. Yes, you have told me, sir. Sir, you have told me that in hydraulic routing, this one, we use Saint Venant's equation, continuity and momentum. When we combine these equations, we call it as Saint Venant's equation. Okay, we call it as Saint Venant's equation. Okay, now many topics are left. Storage characteristics. Okay, important topics. Hydrological channel routing is there. Muskingum equation, one question is there. So we'll discuss that in the next class. Okay, that will be our last class, but no issues. Very minor topic, not so important. So till here you can say that almost all hydrology is done. Now only flood routing is there. So in entire hydrology, what we have discussed about precipitation or basic introduction. We have discussed about what we have discussed about your abstraction from precipitations. We have discussed about runoff. Okay, we have discussed about stream flow measurement. We have discussed about hydrographs. What is hydrograph? What is unit hydrograph? All these things we have discussed. We have solved some questions from unit hydrograph also. How to convert DR unit hydrograph into TR unit hydrograph, that we have also discussed. We have discussed about flood. Basically, we are interested in finding peak discharges in flood chapter. How we do it? We have discussed some methods. And in flood routing, sir, we are interested in finding the downstream discharge. If we have upstream discharge, and if I'm interested in finding downstream discharge, so that I will do with the help of your flood routing technique. And in that, basically, sir, we use continuity equation. I have told you this thing. So one very small topics are left that we'll discuss in the last class. Okay. Okay. So this is for today's class. So let's end it. So thank you, everyone.